I want you to imagine just for a second that you are building this massive, intricate city out of Lego bricks.
Oh, I love Legos. Like a huge setup.
Yeah, exactly. We were talking skyscrapers, suspension bridges, little vehicles moving around the streets, just an absolute masterpiece.
Right, right.
But now, picture what happens if the individual bricks you are using were, fundamentally poorly designed. Like some of them are warped, some are just these giant, unmanageable blocks that don't fit anywhere.
That sounds incredibly frustrating.
Oh, it gets worse. Worst of all, someone snuck in overnight and stuck half of your infrastructure together with industrial superglue.
Oh, wow. So that is a structural nightmare right there.
Exactly.
Because if you step back and realize, hey, your suspension bridge needs to be moved like 3 inches to the left to align with the road,
Yeah?
you can't just detach the pieces.
Nope, they're completely fused.
Right. So the whole structure is paralyzed. You would literally have to snap the bricks and tear down the entire wall just to change a single detail.
And that frustrating, rigid, unbreakable Lego city is, it's the perfect metaphor for what it is like to work with poorly designed software.
It really is. The super glue is the perfect analogy.
I am so ready to understand this today, mostly because, I want to know why my banking app crashed 3 separate times yesterday when all I wanted to do was check my balance.
Yeah, that is always a fun experience.
Truly. So, in the world of coding, those individual Lego bricks are called methods. And today, for this deep dive, we are cracking open the architectural blueprints of software design from Chapter 4, Design of Methods.
Such a great source text.
It is. We are going to figure out what makes an app resilient versus what makes it just, a fragile mess. We are going to master the two foundational pillars of software stability, which are cohesion and coupling.
And it is a critical distinction to make, honestly,
Mm-hmm.
because writing code, and by that I mean just typing commands to get a machine to do a thing, is actually relatively straightforward.
Right. You can kind of just force it to work.
Exactly. You can brute force a solution. But designing sustainable, resilient code that survives for years, that is an art form.
It really is.
It requires deep, forward-thinking architecture. So for anyone listening, whether you manage a team of engineers or you're just a curious person wondering why our digital world sometimes feels like it's held together by duct tape.
Or super glue.
Or super glue, yes.
Yeah.
This deep dive is how you start to see the matrix of software stability.
Okay, let's unpack this. Let's start with the basic building block. Because before we can even look at how these methods, these, individual Lego bricks interact to build a city, we need to understand what a method is actually supposed to do in total isolation.
Right. So at its most basic level, a method is the smallest independently referenced unit of code that handles a specific task.
So it's like a single action.
Exactly. You can think of it as a highly concentrated software action. It takes some information from its environment, processes it, and then spits out a result, or maybe it updates the state of the system.
Okay, making sense so far.
But the concept that really makes this work for human developers is something called procedural abstraction.
Procedural abstraction. Okay, let's break that down without the jargon. Because it sounds like a fancy way of saying, we are hiding the messy, chaotic reality of how something works behind a very simple, clean interface.
That is the absolute core of it, yes. You want to hide the how and only present the what.
Right.
Our sources use the idea of generating a web address, a URL, to explain this. Let's say you need a piece of code to construct a standard web link.
Okay, pretty common task.
Very common.
Yeah.
So you design the inputs, what we in the industry call parameters, based purely on what is strictly necessary to build that link.
Right, so you'd need the basic parts of a URL.
Exactly. You might ask the system to provide a prefix, a separator, and maybe a search query.
You feed it those 3 ingredients and boom, it hands you a working web link.
Yep, it's that simple.
But our source material points at a massive trap here. Developers sometimes try to make a method more general or, future-proof by adding completely irrelevant inputs.
Oh, this happens all the time.
Like, what if you suddenly ask that URL builder for a font name or a text size? A web link has absolutely nothing to do with fonts.
No, it doesn't. And adding that irrelevant information completely shatters the abstraction.
It just ruins it.
It does. The method's instructions become so confusing to anyone else trying to use it. The inputs of a method should abstract away the data perfectly, no more, no less.
I actually have an analogy for this. A good method should operate like a kitchen blender.
Okay, I like where this is going.
So you walk up, you pass in the fruit. Those are your inputs or your parameters. The blender entirely encapsulates or hides the terrifying, chaotic spinning blades inside.
Right, you don't want to see the blades.
Exactly. It just hands you a smoothie. That is procedural abstraction. But if you walk up to that blender and before it blends your strawberries, the control panel demands to know your shoe
Oh
size
my gosh,
or your
yes.
social security number. The design is fundamentally broken.
The blender is a fantastic way to visualize a concept we call the black box.
The black box, right?
Yeah. A well-architected method operates exactly like a black box governed by an ironclad contract. And we call the terms of this contract preconditions and postconditions.
So just to clarify, the preconditions are what the method absolutely requires to function without crashing, like needing actual fruit, not rocks, for the blender.
Yes, exactly. No rocks in the blender.
And the postconditions are what it guarantees to spit out the smoothie.
Exactly. If you meet the preconditions, the method promises the postconditions will be delivered.
You don't need to know the RPM of the spinning blades.
No, you just need to trust the contract. And as an architect, designing that contract is arguably way more important than writing the actual internal code.
Which brings us to the internal mechanics. If a method is this independent black box, what should the instructions inside it actually look like?
And that introduces the first of our two major design pillars, cohesion.
Cohesion.
Yes. Cohesion characterizes the internal harmony of your code. It measures the degree of interaction and relatedness between the instructions living inside that single module.
The blueprints we are looking at break cohesion down into a spectrum, right? Basically from the absolute worst way to design a method to the absolute best.
Right, it's a sliding scale.
So at the very bottom, the lowest tier, you have coincidental cohesion, which, from the text, sounds like a method is just a dumping ground for completely unrelated tasks.
It really is. Think of it like the junk drawer in your kitchen.
Oh, I have one of those.
Everyone does. You have batteries, a screwdriver, loose change, maybe a takeout menu.
A completely random assortment.
Exactly. They're in the same box, but they have zero relationship to one another.
Makes sense.
Now, moving slightly up the ladder, you find temporal cohesion. This is where tasks are bundled into one method simply because they happen at the same time.
So, like a morning routine, taking a shower, making coffee, and feeding the dog. They are totally unrelated tasks, but you bundle them together because they all happen at like 7 a.m.
That's a great way to put it.
But in software, what does that actually look like?
Well, the most common example is a startup sequence, often called a constructor in object-oriented programming.
Okay, the constructor.
Right. When an app first opens, it might need to draw the graphics on your screen, open a security connection to a database, and then set your user preferences to default.
Okay, I see. Structurally, graphics and databases have nothing in common.
Nothing at all. But they all must happen at the exact same moment the app launches to create a clean initial state.
So they are only related by the clock. That makes total sense. But the blueprints suggest we want to climb even higher up the cohesion ladder.
We do. We eventually reach something called communicational cohesion.
Communicational cohesion.
Right. This is where the design starts getting genuinely strong. In communicational cohesion, the internal tasks might be different, but they operate on the exact same piece of data.
Okay, can you give an example of that?
Sure. Imagine a method designed to audit a student's academic record. It does two things. It calculates their final grade point average, and it verifies if they have met the requirements to graduate.
Oh, got it. So there are two distinct jobs, but they share a theme because they are both reading the exact same student transcript.
Correct. They use the same input. And if we step one rung higher, we hit sequential cohesion.
Sequential, like a sequence.
Exactly. This is where one task cannot possibly be completed without the other in a very specific order.
Okay.
Think of a military radar system trying to track a moving object. First, the method must calculate the object's current trajectory.
Right.
Then, it uses that newly computed trajectory as the direct input to predict its future location.
So the two tasks are just inseparably chained together.
Yes, the output of part A is literally the fuel for part B.
Okay. And sitting at the absolute top of the spectrum, the gold standard, is functional cohesion.
The holy grail.
Right. This is where the method just does one singular complex task perfectly. It calculates the task and nothing else. It saves the file and nothing else.
Exactly.
But wait, hold on. I'm looking at the spectrum and seeing a massive contradiction here.
Oh, so?
Well, you just praised the student record audit for doing two jobs, calculating grades and checking graduation.
I did, yes.
But then you say the gold standard of coding is a method that only does one single thing. Aren't you kind of contradicting yourself? Like, hey, is doing multiple things bad or not?
Ah, okay. That is the exact trap many junior developers fall into.
Really?
Yes. They think cohesion is just counting the number of actions. It is not about the raw number of tasks at all. It is entirely about their conceptual relatedness.
Unpack that for me. How can doing 5 things be highly cohesive?
Think back to the temporal cohesion example, the app startup sequence.
The one doing graphics and databases.
Right. It does a dozen completely unrelated chores. Technically, the relatedness of those tasks is incredibly low.
Because it's just the junk drawer of the morning routine.
Exactly. But hiding all those messy, ad hoc startup details inside a single launch app method dramatically improves the readability of the rest of the software.
Oh, I see. You don't want those startup chores bleeding into the rest of your system.
Exactly. You isolate the mess. You accept a lower level of cohesion in that one specific method because it protects the integrity of everything else.
That is fascinating. So you are saying design is always a negotiation.
Always. You seek the highest level of cohesion that makes practical sense for the problem you are solving without creating an administrative nightmare.
Okay, so let's say we nail it. We build the perfect, singular Lego brick. It calculates sales tax flawlessly. It is functionally cohesive.
A beautiful brick?
But here is the flaw in isolation. One perfect brick doesn't make a city. The second I snap that text calculating brick onto a shopping cart brick, I am creating a dependency.
Yes, you are.
They have to talk to each other. So how do we manage that?
That unavoidable collaboration introduces our second foundational pillar, which is coupling.
Coupling. Okay, here's where it gets really interesting.
Yes. If cohesion is about the internal harmony of a single method, coupling is about its external dependencies. It measures the degree to which one module relies on the inner workings of another module.
And just like cohesion, there is a right way to couple things, and a totally disastrous way.
Very disastrous.
Our sources highlight a statistical math example to show what good loose coupling looks like. Imagine you are writing a piece of software to compute the standard deviation of a massive data set.
Right, and to calculate a standard deviation, the mathematical formula requires you to first find the average, or the mean of all the numbers.
So you could just write the logic to find the average right there inside the standard deviation method. Just jam it all into one massive block of math.
You could, but the code would become a visually dense, unreadable wall of text.
Just awful to look at.
Exactly. The underlying statistical formula gets totally buried in the mechanics of adding up numbers. The elegant approach, the loosely coupled approach, is to extract the average calculation into its own completely separate method.
So your standard deviation method simply shouts out to the system, hey, run the average method and give me the result.
Exactly.
Which is brilliant for 2 reasons. First, the standard deviation code is now incredibly easy to read.
Much cleaner.
And second, because the coupling is loose, you can completely gut and rewrite the average method later. Like, maybe you find a lightning-fast new algorithm to do it, and the standard deviation code doesn't care at all.
Nope, it won't break.
It doesn't need to know how the average is calculated, only that it returns the right number.
That is the ultimate goal of treating collaborating methods as black boxes. Loose, intentional coupling makes your software reusable and flexible.
But ad hoc, tight coupling.
That is what causes software to shatter when you try to update it. It's the superglue on the Lego bricks.
The blueprints outline a few types of bad coupling, and honestly, they read like a horror story for developers.
You really do. Let's start with something called control coupling.
Okay, what's that?
They give an example of a method that requires the system to pass in a mysterious number, a flag.
Passing a magic flag, like sending a 1, a 2, or a 3.
Right, to dictate the logic inside a method. The code essentially says if the caller sends a 1, I will do task A. If they send a 2, I will do task B.
Why is that considered such a toxic design? It sounds simple.
Because it forces the caller of the method to understand the internal guts of the black box.
Oh, it breaks the abstraction.
Yes. You are breaking the procedural abstraction. The developer, using the method, has to hold a mental map in their head. I know that internally, a 1 means process the payment and a 2 means cancel the order.
That sounds exhausting.
It is. The two separate areas of the software are now tightly, dangerously tangled together. The cognitive load on the developer becomes immense.
You completely lose the trust in the contract.
Exactly.
But it gets worse. There is also data coupling, or what they call stamp coupling.
Oh, this one is so common.
This happens when you pass way more information to a method than it actually needs to do its job.
Right.
For anyone unfamiliar, imagine a massive spreadsheet where every row is a student and every column is a test score. In coding, that is essentially a 2-dimensional array.
And imagine a method designed to calculate the final grade for just one single student. But instead of handing the method just that one student's row, the system hands over the entire massive spreadsheet containing the data for the whole university.
Oh my gosh, that is like handing a barista your entire physical wallet, your passport, and your house keys just so they can take out $3 for a coffee.
That is a perfect analogy.
It is a massive security vulnerability.
Think about the fallout of that design.
Mm.
You are exposing the entire university's data to accidental modification.
Right.
If a junior developer makes a tiny error in that grading method, it might accidentally overwrite the grades of 1,000 other students.
And when you are debugging, trying to find out why a student's home address got deleted, you have to dig through a math function that had no business even seeing the address in the first place.
Exactly. You should only ever pass the exact $3, the specific data that the method requires.
Okay, the barista wallet analogy makes the danger so clear.
Good. Because there's one final horror story here. Instance variable coupling.
Instance variable coupling, okay.
This involves shared state. To explain this simply, imagine an instance variable as a sticky note on the office fridge.
And a sticky note on the fridge.
Right. Any
Yep.
method can write on it, and any method can read it.
Okay, our sources use a search operation to illustrate the danger here. Imagine a command called findMax that searches a massive list of files and finds the largest one.
Right.
But instead of returning the result directly to whoever asked, it writes the location of that largest file on the sticky note on the fridge, the instance variable. It just parks the data there for another part of the program to use later.
Which seems super convenient at first glance.
Right. It is like leaving a message for your coworker.
But what happens if another totally unrelated method also uses that same sticky note to do its job?
Oh no, chaos. Pure chaos.
Exactly. Race conditions. If a user clicks the Find Max button, but then accidentally triggers a different search, before the system grabs the first result off the sticky note, the data is overwritten.
The first result is just gone, erased.
Yes. And the system will silently proceed using the wrong information.
Because the methods are secretly coupled through the shared sticky note, and they have to be executed in a very specific, undocumented chronological order to work.
Exactly. That invisible dependency completely destroys reusability.
Yeah.
You cannot just pick up that Find Max method and use it in a new app because it is hopelessly tangled up with the sticky note on the fridge.
Right.
It creates a devastating ripple effect. A tiny change in one module ripples out and causes unpredictable, silent bugs across the entire ecosystem.
It's the industrial superglue on the Lego bricks all over again. You try to snap one piece off to fix it, and you inadvertently tear the whole wall down.
Which brings us face to face with the inevitable reality of engineering. We know the theory. We want high internal cohesion, and we want loose external coupling.
But the real world is messy.
Very messy. Deadlines loom. Requirements shift at the last minute. Developers take shortcuts to get the product shipped.
So how do we spot when our code is failing these ideals? If the bugs are silent, how do we know the superglue is there before the wall collapses?
The blueprints introduce a fantastic industry term for this, actually code smells.
Code smells. I love that.
Code smells are surface indications that suggest a much deeper rot in your architecture. The code might technically work today, but the smell warns you that it is structurally unsound.
The sources list some classic smells. Using those global sticky note variables is a big one.
Huge smell.
Methods that require a massive barista wallet list of inputs, classes that only hold raw data and perform no actual actions, and my absolute personal favorite, suspiciously extensive comments.
Yes. If a developer has to write a 3-paragraph essay in the comments to explain what a 6-line block of code is doing, the code itself is a structural disaster.
Because comments should explain why a business decision was made, not how the code operates, right?
Exactly. If the mechanics are too confusing to read natively, the architecture just needs to be redesigned.
The blueprints give a brilliant example of a code smell involving nested loops.
Yes, the order list example.
Right. Let's walk through the reality of this one. Imagine a retail software system reviewing every single order a store received that day.
Okay, pretty standard.
The external system looks at an order, reaches deep inside that order's private data, pulls out an internal list of purchased items, and iterates through every single item to calculate the total sales tax.
Now, to a novice programmer, that looks totally fine.
Sure, the math is correct. The tax is calculated.
But structurally, it completely violates data encapsulation. The external system is crossing boundaries, reaching deep into the private inner workings of the order object and doing the math on its behalf.
It is exactly like a store manager walking up to a cashier, reaching into the cashier's brain to pull out the prices of the items, doing the addition in their own head, and then handing the total back to the cashier.
That is a wildly inefficient and invasive way to manage a store.
Right. The manager should just ask the cashier, what is the total?
Exactly. And the refactor, the architectural fix for this code smell, is to empower the object. You introduce a new service command inside the order object itself. You basically give the cashier a calculator.
So the order object does its own internal math.
Precisely. Now, the external system just iterates over the day's orders and asks each one, what is your total value?
And the invasive inner loop is entirely eliminated.
Yes. The code becomes highly readable, the private item data is protected from external tampering, and the order object becomes highly cohesive because it manages its own state.
That sounds like a massive victory for clean design.
It is.
But, you know, it makes me wonder, if I spend all my time hunting down every code smell, constantly refactoring my system to achieve perfectly loose coupling and perfectly high cohesion, do I reach nirvana? Like, does perfect code actually exist?
That is the million-dollar question in software engineering. And the harsh truth is no. Perfection is a myth.
But wait, really, we just spent all this time outlining the perfect blueprints. Why can't we achieve it?
Because software architecture is a perpetual negotiation of trade-offs. You literally cannot have zero coupling if you want independent methods to collaborate and solve a complex problem.
Because they have to talk.
Exactly. The absolute second they communicate, they are coupled. The blueprints illustrate this beautifully with a final refactoring example regarding student grades.
Right, the GPA calculation.
Initially, a developer might write a messy, sprawling loop that calculates everyone's GPA directly from a raw spreadsheet of grades.
And recognizing the code smell, they decide to refactor it.
Right. They extract all that complex logic and bundle it into a brand new, highly cohesive object called the academic record.
Which gives the system a beautiful, clean command to just ask for the GPA.
It does. It drastically improves human readability. But look at what it cost.
What do you mean?
You had to invent entirely new structural layers in your software. You create a new object, which requires memory, and it introduces new, deliberate coupling between the system and this new academic record class.
Ah, I see it now. You are trading code complexity, the messy math loop, for structural complexity, managing more interconnected objects.
Exactly. Good modularity is not about achieving some theoretical academic perfection. It is a pragmatic balancing act.
So you have to weigh the options.
Always. As an architect, you prioritize sustainability. You look at the code and ask yourself, is this trade-off going to make this system easier to debug and expand 6 months from now when half the original team has moved on?
Right, because someone else has to read it.
Exactly. That foresight is what separates someone who just types code from a true software architect.
So what does this all mean for you listening? It means that the apps and systems we rely on every day aren't just written, they are architected.
Very intentionally.
Cohesion is the internal gravity that ensures your individual Lego block is strong and serves a definitive purpose. And loose coupling is what ensures you can snap that brick off and swap it out for a better one without tearing down the entire city infrastructure.
And whether you are debugging a script this afternoon or you are an executive managing a department of developers, recognizing these patterns is your competitive advantage.
Spotting a structural code smell, recognizing the danger of a barista wallet data transfer, or understanding when to tolerate messy temporal cohesion at startup, that is your shortcut to being a deeply analytical, systems-level thinker.
It really is about seeing the invisible forces that hold complex systems together.
Absolutely.
And actually, I want to leave you with one final thought to mull over, extending far beyond just computer science.
Where are you going with this?
Think about the human organizations you interact with. Think about the company you work for.
Okay, I'm picturing it.
Imagine a department that is incredibly cohesive. They are laser-focused on a single vital goal. But their processes are tightly coupled to 3 other departments.
Ooh, wow.
They require endless approval loops, shared access to the same messy spreadsheets, and constant micromanagement from outside managers just to execute their one goal.
The ripple effect of a bad process. Progress would completely halt. It's the super glue all over again.
Yes. The principles of architecture aren't just for machines. So ask yourself, can the concepts of functional cohesion and loose coupling be used to debug the human workflows, the communication bottlenecks, and the teams we interact with every single day?
That is a phenomenal perspective to keep in mind the next time you are stuck in a dependency loop at work. Until next time, keep diving deep.